Okay. And so this has led to many rapid advances on the methodological and applied front. So what this means is, okay, so there's been a lot of advancement in causal inference in identifying new causal estimates, so things that we'd like to estimate that have some causal significance. New identification strategies, so new ways of linking these causal estimates to observational data, so data that you have at hand, and also in terms of developing new estimators. And a lot of this work has been motivated and somehow very fruitfully exploits a certain interface that exists between machine learning and causal inference. So they're trying to use powerful black box predictors, so things like neural networks, in order to answer certain types of causal questions. And we'll see a little bit more why this interface exists. But this has led, in whatever this advances in machine learning have led to lots of advances in causal inference. On the other hand, maybe I'll try to convince you that the theoretical foundations of this field still lag far behind. And so maybe you'll see throughout this talk that for fairly basic causal estimates, we don't understand really what are the limits of how well we can estimate them and so on. And in terms of statistical theory, there's lots of things that we don't understand about testing, about adaptation, and so on. So most of the talk will focus on certain basic estimation questions in causal inference. Okay. So the outline for today, I'll tell you a little bit about two papers. The first one will try to develop some minimax theory for an important causal estimate. It's the so-called conditional average treatment effect, or the personalized causal effect, or the heterogeneous causal effect. I'll tell you what it is in a minute, but then we'll try to say, okay, how well can you estimate this quantity? And the second thing, we'll sort of take a step back and say, what are the fundamental limits of what is called, I'll define a certain thing, it's called structure agnostic functional estimation. So how well can you estimate various causal quantities when you're not willing to make classical statistical assumptions like place some smoothness restrictions or place some sparsity restrictions on things. So if you're not willing to make those assumptions, how well can you do? Okay. If you have any questions at any point, just feel free to interrupt. Okay. So let's jump into the first half. This will be trying to tell you a little bit about this problem of estimating heterogeneous causal effects and how well we can do. So maybe when you first start learning about causal inference, the first thing you'll learn about is so-called average treatment effects. So these are average odds ratios or things like that. And these are measuring some notion of what a treatment or a policy does in some global average sense across a population. Right? So these are the most traditional classical causal estimates. So this, maybe if you think about the average treatment effect, it's going to ask a question. It's going to try to answer the question, okay, what would happen if all of you in this room took a drug versus all of you didn't? Right? So if everyone was treated versus none of you were, what would the effect be? Right? So we will look at some average across an entire population. Maybe none of you in this room need any convincing that this can obscure a lot of heterogeneity. So this means that the average effect might be zero, but it might be the case that your treatment helps some subset of the population, but actually harms another subset of the population. Right? So the effect might be zero, but the treatment might actually have an effect. It just might have a positive effect on some strata and some negative effect on a different strata. And this is something that, of course, we'd like to know. It has very useful, so if we understand the variation in these treatment effects, it's going to be useful for many things, and it will in fact help inform policy decisions, inform how we allocate treatment to a population and so on. Right? So this understanding the heterogeneity in the treatment effect can be a useful thing to do. So the question, of course, it's significant even in a randomized controlled trial. So I will tell you a little bit today about how one assesses a heterogeneity or estimates these heterogeneous effects in an observational study. But even in a randomized trial, this question has significance. So if you, for instance, opened up papers associated with the three maybe most popular COVID vaccines. So the first one is the Pfizer vaccine, the second one is the Moderna vaccine, and the third one is the Johnson & Johnson vaccine. So if you associated with each of these vaccines was a randomized controlled trial, and associated with each of these trials is a paper that would have eventually been published. And each of them will somehow summarize the results of this trial. Right? So if you look in these papers, you will see that they don't just tell you what the average effect is. So you should think of this vaccine efficacy as some sort of treatment effect like quantity. they don't just report it as an average across the entire population, but rather stratify that effect in various ways and tell you what it was. And so maybe if you looked, one of the more stunning things about the Moderna trial was that, so these are the results, they stratified it across various groups by age, by gender, by how likely, how at risk you are for getting severe COVID, by race, by all sorts of things. And what they found was this vaccine had roughly not very heterogeneous effect. It was a high effect, and it was relatively stable across various different populations, right? So this is the kind of thing that people would report when they do an RCT, is that not just what is the average treatment effect across the entire population, but across various interesting subgroups, what is this effect? Everyone okay so far? Good. So, and on the other hand, one of the reasons why people preferred the mRNA vaccines early on was that if you had looked for a similar table for the Johnson & Johnson vaccine, you would have seen something. So now you can look at this last column and you'll see much more heterogeneity overall. So they did something similar. They measured something a little different, but maybe the highest level takeaway from their trial was that there was much more variation across different populations, in different countries. So they ran a trial in South Africa and in Brazil and in the United States, and they got pretty heterogeneous effects across the board. Okay, so again, we'd like to understand things like this. So now I'm going to dive in and just formalize the question and then tell you a little bit of, now we'll sort of take a very theoretical lens to this question. Okay, so here's the classical way of formalizing causal questions. We'll start with this causal inference data structure. So what you will observe is, for a set of units, you will observe some set of covariates. We'll use X to denote covariates. A will be a treatment. Treatment will be binary for us. So you either receive a drug or you don't receive a drug, and then you will observe some outcome Y. And so you observe triples of the form X, A, and Y for a bunch of people in a population. Is everyone good so far? Great. So in our COVID example, the X would be something like your age, your country, how at risk are you for getting severe COVID, measured by some set of demographic features again, and so on. Right? So you measure some set of features about everyone in your population that forms the covariates X. A will be whether you received the vaccine or not, and Y will be whether you contracted COVID or not. So maybe in a COVID trial, one could imagine the Y is also a binary quantity. And now we will need a little bit of causal notation or counterfactual notation. So we'll let Y superscript A denote the counterfactual outcome if you receive treatment A. So what would your outcome have been if you received treatment little a? Okay, so in our COVID trial, Y1 would be whether you would have contracted COVID if you had received the vaccine, and Y0 would be if you had not received the vaccine, whether you would have contracted COVID. Okay, and now we will work under the most standard setting. So that is, we're going to try to estimate a causal effect of this form. So something like Y1 minus Y0 using observational data. So it won't necessarily be a randomized control trial. So this needs some set of assumptions. The most common ones are the ones that we'll work under. So the first one is called no unmeasured confounding. So there might be confounders which decide, I don't know, there's differential treatment assignment across different strata of the population, but you've measured all of the important ones. So the way that you mathematically formalize this is that you say that the treatment is independent of the potential outcomes once you stratify your population by the covariates that you've measured. Right? So you have measured all of the useful confounders in this problem. Right? So this assumption is somehow the critical one that will let you estimate causal quantities even though you're not in an RCT. Right? So the second assumption will be, it's called positivity or strong positivity. It says that every individual has some probability of receiving treatment or of being in the control group, right? So of not receiving treatment. And so this probability, the probability of receiving treatment for each individual is bounded away from 0 and 1. Is everyone okay so far? Good. So once you've written all of this, again, the standard, now that we've introduced this counterfactual notation, we can say what we mean by an average treatment effect. It's just the average of Y1 minus the average of Y0 across your population. So it's this quantity. This is, as we were discussing earlier, it's the mean outcome if everyone received treatment versus nobody received treatment. Now, when we say heterogeneous treatment effects, we'll mean something very simple. We mean I'm now going to be interested not in this average quantity, but rather in this quantity tau of x. Tau of x is going to be the conditional expectation of Y1 minus Y0. Right? So that is, you should imagine it as some sort of personalized effect. I'm going to say, if I had some set of covariates, I want to know what is the treatment effect for people who look like me. Right? So I'm going to input my set of covariates and then ask for this function tau of x. And this is going to tell me what is the effect of your vaccine on people who look exactly like me, not on the entire population in some average sense, but rather just for people who look like me. Everyone good so far? Thank you. So then under some standard non-measured confounding assumptions, the same ones that we wrote on the previous slide, this quantity is also identified, and it can be written as a difference of two regression functions. So it'll be useful to think of now, okay, amongst the units who are treated, you can do a regression, so that is compute this conditional expectation. So you can do it amongst the people who are treated and amongst the people who are not treated. That will give you two regression functions, mu1 and mu0. And the personal effect, or the Kate or the heterogeneous effect, is just going to be the difference of these two regression functions. Okay, so this will be the quantity that we'll be interested in estimating. Is everyone okay so far? Okay, so at this point, you should maybe pause and say, okay, why is this at all an interesting question? For sure, for nearly 100 years, we've known how to estimate regression functions at a point. So knowing how to estimate mu1 at a point x, we know essentially a complete theory for this. Under any set of assumptions that you might be interested in writing down, we probably know how hard it is to estimate mu1 of x and mu0 of x. And maybe what is going to make this problem interesting is that you're not interested in estimating either one of them individually, but rather this difference of them. Okay, so let's start off with the basics. So if I were trying to estimate this, what is the most basic way of estimating this? This will be an example of a functional. So in statistics, we'll often call quantities like this a functional. It sort of takes a distribution and summarizes it with a number. Right? That's what a functional is. So the standard principle that one might use to estimate a functional is to use what's called the plug-in principle. So if I want to estimate some quantity like this, one thing I can obviously do is to do two separate regressions, one on the units who are treated, one on the units who are in the control group, and then take their difference. So this is called the plug-in estimator. And this is maybe the first baseline thing that you might try. And I will try to convince you that, okay, there's a set of very reasonable assumptions under which this is not necessarily a very good estimator. And the key idea, and this will be the key thing to take away, at least for the first part of this talk, is that the complexity of this quantity tau of x, this difference of two regression functions, can be very different from the complexity of any one of the regression functions themselves. Right? So the way you should think about it is each of these mu1 and mu0 are measuring some sort of outcome process, and they can be quite wiggly as functions. They can be fairly complex functions. But if you have a drug and say it has a relatively stable effect across the population, then you might imagine that there are settings like that where tau of x will be very simple. Tau of x may be 0 if your drug has no effect. Tau of x is a constant if your drug has constant effect across the population, and so on. So even though the function mu1 and mu0 can be quite wiggly, maybe it's sort of reasonable to hypothesize that tau of x, this difference of these two regression functions, is actually quite smooth. So this is just saying what I just said. And this will be somehow the key idea, that maybe the Kate, or the conditional average treatment effect, is a simpler process to try to model or try to estimate than either of the regression functions themselves. Okay, so one thing that you can notice is that if you think about smoothness, for instance, if mu1 and mu0 have certain smoothness, then for sure tau has at least that amount of smoothness. It could be a lot smoother, but it has at least that amount of smoothness. So just to get some sense of why plug-in estimates maybe are bad, here's sort of a cartoon figure. So you can imagine here's a case where this is the true outcome. So you have some drug. This is the outcome process. The drug has no effect. So both mu1 and mu0 look like that wiggly function over there. Your drug has no effect whatsoever. Now you'll observe some data. So you will see some set of units who are treated, and you'll see their corresponding outcomes. And then you'll see some control units who didn't receive the treatment. You'll see their corresponding outcome. And so maybe the data that you observe kind of looks like that. And if you try to fit each of these two functions separately, then because each of these functions is pretty wiggly, you might do a bad job. And then when you take the difference, okay, you might get a relatively bad estimate. And this is maybe the intuition for why a plugin might be bad. It's trying to somehow separately estimate mu1 and mu0. And maybe you could do a little bit better than that. Everyone okay so far? Good. Okay. So maybe to set the stage, okay, what is the best performance that we could hope for? How well could we hope to do in general? So to set some benchmark, maybe you should imagine this hypothetical situation where you have access to some oracle. This oracle, instead of telling you only one of the two potential outcomes, so causal inference is usually hard because each unit only receives a treatment or is in the control group. You never see both outcomes for a unit. So suppose for now you had access to this oracle that had told you the difference of these two potential outcomes. So he told you y1 minus y0. And then if you knew both of these potential outcomes, you could regress it on x and try to estimate this quantity tau of x. This would be quite a nice thing to be able to do. And we'll call this oracle tau star. And so this will give us some baseline. This is somehow the best we could hope for. If your tau function, this kate function, is gamma smooth, so now you should think of it as gamma smooth in some Holder sense, then you imagine some typical non-parametric rate. Right? So the best that you could hope for would look like this. It's a n to the minus 2 gamma over 2 gamma plus t. It's a non-parametric rate. It gets better as gamma gets bigger, it gets worse as the dimension gets bigger. Right? So this is some standard rate. So if your function was in fact gamma smooth, and I was an oracle that knew the difference of each of these potential outcomes, then this is the best rate I could get. Is everyone good so far? Good. All right, so this oracle, of course, is somehow implicitly exploiting all of this smoothness in the difference, right? Since it knows the differences, if the differences are smooth, it gets a much faster rate. And so now the question is, how do we mimic an oracle that looks like that? So one thing that one can do is to try to take some inspiration from the average treatment effect. So the average treatment effect, you should think of it as, it's kind of like the conditional average treatment over the entire population is the average treatment effect. So if you imagine a little bin around some point of interest, then maybe the average treatment effect over that little bin is the quantity that we're interested in. It's this tau quantity. Right? So as I was saying, this kate quantity that we're trying to estimate is roughly like the average treatment effect over a little bin around the point you're interested in. And for estimating average treatment effects, we know a lot of things. We know that these plug-in estimators are typically suboptimal. We know something which are called first-order corrections or one-step corrections. They're called doubly robust methods, and they can be efficient in some cases, which means they can mimic some sort of oracle for estimating the average treatment effect in some cases. So there are these one-step corrections that improve on the plug-in estimate. And then we know something like there are so-called higher-order estimators which improve on these one-step estimators, and they attain minimax optimality over various smoothness classes. Right? So for the ATE, there's maybe something that's more like a complete picture that we understand, and we'd like to understand what's the analogous thing for estimating a conditional average treatment effect. So let me now try to explain to you roughly at least what is the doubly robust estimator, and then we'll try to mimic it for the kate, and then we'll try to improve it just like the higher order estimators do. So the high level intuition for what goes on here is that when you're trying to estimate a functional, so you should imagine you're trying to estimate some functional of a distribution. You should think of it as the psi of p. The plug-in estimator says, okay, first I'll estimate whatever I can, the distribution p hat, and then I'll plug it into this formula. So if I want to estimate some quantity psi of p, I'll estimate the distribution and then plug it in. So that would be the first term here would be what we usually call the plug-in estimator. And then if you did some sort of Taylor expansion, then you would see that, okay, this is some sort of functional Taylor expansion, then you would get a first order term. It would be something like the derivative of this functional with respect to its argument times p minus p hat. And the crucial point is whatever this term is linear. By linear, I mean it's the expectation of some function that you know minus some constant. Right? So, and we know how to estimate expectations. If I give you a sample from the distribution, you just take an average and you can estimate this linear term. So you can hope to improve on a plug-in estimate by trying to estimate this linear term in this expansion. And it's very easy to estimate the linear term as long as you know what that derivative is, because it's just a sample average. You can estimate it by a sample average. And then once you do that, rather than get some sort of first order error, which a plugin would have, you might get some second order error. And so you would improve on the plugin estimator. So this is the idea of one-step corrections in statistics or first order estimators or doubly robust estimators. Is everyone roughly okay so far? Okay. So how does this work actually? So when you are doing this for the average treatment effect, it'll turn out that So you can write the doubly robust estimator for the average treatment effect as an average of something. It'll be called an estimated pseudo outcome. Doesn't matter what this is exactly, but the idea will be that you'll first take a plug-in estimator. So the doubly robust estimator of the average treatment effect, again, it's a very classical object. It looks like a plug-in estimator. So the first term is something like a difference of two regression functions averaged over your population. So that would be the plug-in estimate of the ATE. And then you add to it this one-step correction. In this case, this one-step correction will take some form. It's called IPW weighted residuals. So it looks like y minus mu hat weighted with something like 1 over pi, where pi is this propensity score object. Okay, so none of these details matter so much, but there is this one-step correction that you can do to estimate the average treatment effect, and it'll have this miraculous property that the estimate of the average treatment effect will have some variance which looks like 1 over n, and its bias, rather than being first order, will now look like this product of two biases. So you get some squaring behavior, which is maybe what you would have expected from here, right? So you get some second order term here, and you'll get that equivalent second order term here. It'll just depend on how well you've estimated these two nuisance functions. So you should imagine in your head, I'm going to try to estimate the average treatment effect. To do this, I will do a regression, and I will estimate this quantity called the propensity score. I'll put them together in this formula, and then magically I will get these second order guarantees. So rather than depend directly on the error of how well you estimated the nuisance functions, it'll depend on the square of how well you estimate the nuisance functions. And so you get some speeding up by correcting the first order term in a Taylor series. Okay, so the main takeaway for now is, without making any assumptions on mu and pi, you get this guarantee for this so-called doubly robust estimator. Everyone good so far? If I've lost you, maybe you can ask me a question and I'll try to help. Yeah. The little a? Yeah, so there's two of these regression functions. So you have to estimate mu1 and mu0. So those are, little a can be either 1 or 0. It's the worst of the two. Yeah. Yeah, so you should, but whatever it is, it's a product of a propensity score estimation rate and a regression function estimation rate. And so the reason why these are called doubly robust estimators is that you can consistently estimate your functional if you either get the propensity score correct or if you get the regression function correct. So if either of these two terms is small, the product will be small and you will get a consistent functional estimate. Okay, great. Any other questions? Okay, good. So now maybe the intuition should be, to estimate the ATE, I just construct this so-called pseudo outcome and average it over the entire population. For the conditional average treatment effect, instead of averaging it over the entire population, I'm just going to try to regress it on my covariates. That is going to compute some sort of local average for me. Right? So this idea is also quite old. It was first proposed by Mark van der Laan a long time ago. And then more recently, people rediscovered and gave it some slightly more general analysis. And so here's the algorithm that one can use to estimate a conditional average treatment effect. You first, on a separate half of your sample, estimate all of these things, the propensity score and the two regression functions. And now, rather than take the average of, so you construct these pseudo outcomes as before. If you were interested in estimating the ATE, you would average these pseudo outcomes over the entire population. Now, if you're interested in estimating the conditional average treatment effect, you instead regress it on X. Right? So in some separate test sample, you compute an estimate of the kit by averaging these pseudo outcomes conditionally over the X's. Everyone roughly okay? So if you wanted to estimate the ATE, you would construct pseudo outcomes. They have this nice double robust property. You would average them over the entire population. If you want to estimate the kit instead, you try to do some sort of local average instead. Everyone approximately okay? Good. Okay, so what do we know about this? So the main thing that you would get from this, if you tried to do this analysis and you made some various assumptions, it would have the following property. You would get the estimate of the kit would now depend, you would get some bound that looked like the oracle. The first term is whatever the oracle gets, right? That's the n to the minus 2 over 2 gamma over 2 gamma plus t. And you would now get an additional penalty. Since you're not an oracle and you don't know these nuisance functions perfectly, you pay some price for having to estimate them. But the nice thing would be that that price would be quadratic, right? So it would look second order. And in particular, if you estimated those nuisance functions at a sufficiently fast rate, then your functional estimate would behave like you would get the same rate as the oracle. So your functional estimate would be efficient in a certain sense. Okay, so maybe the takeaway should just be, if these functions are sufficiently smooth and you estimated them sufficiently well, then you put it together through this so-called DR learner, then you would get some guarantee that would say you would estimate the Kate at that rate. Okay, and so maybe now we can finally ask the question that we wanted to ask, which is this the best that we could hope for, or could we improve such an estimate? And one way to try to answer this question, and this will be somehow a recurring theme in both parts of the talk, is that we'll try to look at this through this lens of minimax optimality. So here, a natural question is to say, suppose I'm willing to assume that pi has some smoothness alpha, mu has some smoothness beta, and the Kate itself has some smoothness gamma, then what's the best possible rate that you could hope for? In particular, can you tell me something about the so-called minimax rate, which is what's the squared error of the best possible estimator on the hardest problem in this collection of problems, which are defined by these smoothness constraints? Everyone okay so far? So I've maybe high level, I've told you what the Kate is. I've told you about one possible estimator of the Kate, which is this DR learner, and told you it achieves this rate. And now we're just asking, is this the best we could do? The difference is gamma smooth. The propensity score, so the regression functions mu1 and mu2 are beta smooth, and the propensity score is alpha smooth. So gamma will typically be bigger than beta, but that's the only constraint. Yeah.
Clarification, so is the second one minimax of X, or you use pointer, or
I'm interested in estimating it at some fixed point. You can get L infinity bounds that look like this. So that is at all points X in your support, you will get some rate, but it'll look the same as this.
So just one more clarification about the result above. So is this kind of somehow assuming that alpha, beta, and gamma are known, or you somehow estimating the data at what rate?
So part of why the so-called double machine learning or DR learner or first order things are nice is that you just plug in your best guess for mu hat and your best guess for pi hat. Those are just regression problems. So you can tune them by cross validation, and then you put them in here and you get this rate. So it is data adaptive, not assuming you know any of those things. You don't have to know even gamma. Yeah.
Yeah. How the upper bound in this theorem compared to the one in Dow 2020, the new paper? They also do minimax estimation for conditional treatment effect.
Not assuming smoothness and doing something different. So it's sort of kind of technical, but they're doing fixed design versions of these things where the rates are completely different because the design is basically fixed. So maybe part of why functional estimation gets a little tricky and interesting is because when you have a random design, you get faster rates. And so that you'll only see that in this kind of model, but you should ask me again offline. Good. All right. Other questions? Okay, good. So before I answer the question of whether this estimator is minimax optimal and tell you what the minimax rate is, maybe it's worthwhile going into a little bit of the history of functional estimation problems. They're a very interesting set of problems in statistics, and maybe the first non-linear functionals, so things that kind of look like these causal effects, were studied. The simplest example is the following question. I give you samples from a density x1 through xn come from some density p, and let's say this density is S smooth. And the question that maybe it goes back to Charles Stein, that Charles Stein was interested in answering was just how well can you estimate a functional? So what is a functional now? It's some one-dimensional object. So for instance, let's look at the integral of p squared. Right? Or you could, if you like, think about integral of p times log p, which would be something like the entropy or something else. Right? So these are functional estimation questions rather than, I'm not interested in estimating the density itself, but rather I'm interested in estimating this one number. It's the integral of p squared or the entropy of this distribution and so on. So the question that people were interested in is this a much, much simpler problem? Do I get sort of rates that look like the estimation of a one-dimensional parameter for estimating functionals? Or if so, when do I get rates that look like that, right? So what Bickel and Ritov showed was, no, you don't always get rates that look like you're estimating a one-dimensional parameter, but sometimes you do. And so they showed, for instance, if you were interested in estimating something like the integral of p squared, the minimax rate looks like this, looks like the worst of 1 over n. So 1 over n is, if I was estimating a one-dimensional parameter, I should expect a rate that looks like 1 over n, and a so-called functional estimation rate, which is n to the minus 8s over 4s plus t. So if you compared it to, it's much, much faster than the rate at which you can estimate the distribution itself. So this functional estimation rate is much faster. And they showed that you can attain this rate. And in particular, you will get root n rates. So it will behave like you're estimating a one-dimensional quantity if you have enough smoothness. But otherwise, you will get this super fast rate, which is n to the minus 8s over 4s plus t. Right? And you can compare this and say, okay, what do one-step corrections do? So we maybe sort of thought about plugins and said plugins are suboptimal. You could do this one-step correction. And they showed that one-step corrections don't attain this bound. They attain a slower rate when s is bigger than d over 2. So you have a lot of smoothness, then you will still get root n rates. And plugins first-order estimators can be efficient, but in general, they don't attain the minimax rate. They have a worse threshold for when they are efficient. And when they're not efficient, they attain this much slower rate, which is n to the minus 4s over 2s plus t. Kind of like you lost half of your smoothness somewhere. Okay. This result led to lots of follow-up work, and people started thinking about how do you estimate other nonlinear functionals, how do you estimate functionals in the Gaussian sequence model, how do you estimate functionals in the white noise model, and so on. And there's some parallel theory for all of this. And maybe for now, the key takeaway should just be, if you're interested in estimating a functional, then first-order estimates are usually going to be suboptimal over smoothness classes, and you need some sort of higher-order correction. So they constructed a so-called second-order U statistic. It's not just an average of stuff, but rather an average of products of stuff, and that attained this minimax rate. Okay, so everyone roughly okay with the history? Good. So what's the result of our paper? Well, we just gave some analogous characterization for what the minimax rate is for this Kate object. To be clear, the Kate, unlike the average treatment effect, it's not exactly an integral of something over the entire domain. It has some other things going on. So it's a little bit less clear that it's even a functional that's like one of the ones I just talked about. So let's see what's going to happen. So suppose that the density F satisfies some set of conditions. You should, for the sake of this talk and for most of the paper, we just assume that you know the covariate density F. And so now there's some propensity score pi, which is alpha smooth. There are these regressions, mu0 and mu1. We'll just assume mu0 is beta smooth. And tau, which is the thing that you're trying to estimate, is gamma smooth. And then what we showed was that the minimax rate, so you can attain it, and there's a lower bound that says you can't do any better, looks like this. It looks like, so if you ignore the portion in red, then it looks like a standard functional estimation rate, but S will be alpha plus beta over 2. So it will be the average of the smoothness of the propensity score and the regression function. So if you ignore the red term, then you get a standard functional estimation rate, but the estimation rate for the Kate is actually a little bit worse. And it mixes some squared estimation rate. So this is the way that gamma comes into this rate. It mixes, it doesn't look like a functional estimation rate for gamma. It looks like a regular estimation rate for gamma, and it mixes that with a functional estimation rate for alpha and beta. And so this was the result of our paper, just gives what this minimax rate is exactly. And maybe for now, if you're not super familiar with these things, the only thing you should take away is that the minimax rate now has some hybrid effect to it. There's something which looks like a standard estimation rate that depends on the smoothness of the Kate. And then there's a functional estimation rate which depends on the smoothness of these two nuisance functions. So I can leave it here for a second, but if you have questions.
What is the estimate?
I'll tell you in a minute. It's not the first order thing, but I'll tell you what it is in 1 minute. Okay, so Arash, how much time do I have? A lot. Okay, that's good. All right, so then let me show you a picture just so that some of these rates kind of start to make a little bit more sense. So if you, wow, you can't see anything, but if you could see something, it would be this curve down here. So what is it? It's just saying, so I'm plotting for you as a function of the smoothness on the x-axis, the mean squared error that you would achieve. So maybe the first thing to take away is, okay, well, this gray line over here is this function n to the minus 2 gamma over 2 gamma plus t. This is the oracle rate. So if you knew y1 minus y0, or essentially you knew your nuisance functions, then you would get some rates that look like this. The plugin estimator will achieve this much slower rate. It will achieve the rate up there. The DR learner that I told you about achieves a slightly faster rate because it improves on this plugin by sort of squaring its error rate, and it will achieve this rate that looks like this. And so if you have enough smoothness, it will attain the oracle rate. It will start to behave like the oracle once you have enough smoothness, but if you don't, it'll be worse than this oracle. And then the minimax rate is given by this purple line. It's faster than the rate that the first order estimator gets, but it is in some cases slower than the oracle. So what all of this is saying is that if you don't have enough smoothness, you can't attain this oracle benchmark. The correct rate is instead given by this purple line up there. Okay. This is just plotting for you those rates. So you should think of it as plugin never attains oracle rates. First order estimator attains oracle rates for sufficient amounts of smoothness. And then these higher order estimators that I'll tell you about will attain this purple line. Okay. Which is the correct minimax rate. Okay, so let me tell you a little bit about how we derive lower bounds, and then I'll tell you a little bit about how we derive upper bounds. So what are the main ingredients that go into deriving minimax lower bounds? So what makes functional estimation problems interesting from a theoretical perspective is that the lower bounds often involve mixtures. So what you're going to do is you're going to construct these two mixtures. So one of them will be a mixture where the functional takes a small value, and one of them will be a mixture over distributions where the functional takes a large value. So you'll construct these two pairs, and then you will try to argue that they're actually very similar. So in some sense, there's some distance, we'll bound something like the Hellinger distance between these two mixtures and try to argue that it's small. And so what this means is that there's this collection of distributions where the functional takes a small value, and there's this collection of distributions where this functional, so the kate, takes a large value, and you can't distinguish them because they're very close in some Hellinger sense. And so if you can achieve all of these things, where you construct this pair of mixtures, where some distance between these mixtures is small, but the functional takes very different values on them, then you've attained you've achieved something nice, which is you've proven a strong lower bound. And so this is all maybe roughly formalized in. If you open up Sivakov's book, it's an old book. If you open it up, you will see some form. He calls it testing of fuzzy hypotheses. So you'll take your model class, you will construct two mixtures, P lambda and Q lambda. You'll argue that their Hellinger distance is small, but you'll argue that the functional, which is psi that you're interested in, is very different on the two sets of distributions. So psi is separated by at least S. And then if you can achieve all of these things, then you will get a lower bound of roughly order S squared. Okay, so this is the so-called method of two fuzzy hypotheses, and this will be useful for us. And so what we will do is I will maybe just very quickly tell you what the distributions we construct look like. So under the null, I'll make the kate non-zero at this point. So I'm interested in estimating the local average treatment effect at this point x0. I'll put a little bump there, and then you will make your regression function. So one of them will wiggle, so the propensity score will stay constant, the regression function will wiggle, and then under the alternate, you will do something else where you'll make the kate 0, you will wiggle both of the functions. And now if you do all of this very carefully, there's some method to all of this madness, but once you construct these mixtures and do this argument, you will see that this will show you that the lower bound that I stated for you is the right lower bound. So maybe the only high-level takeaway that you should get from this is, if you're used to something like Lecombe's method, then the way that we usually get lower bounds in parameter estimation problems is we say, here's a distribution, here's another distribution, I'll calculate some sort of divergence between them, and I will get a lower bound. When you're trying to do this for functional estimation problems, you have to be very careful and use mixtures under the null and mixtures under the alternate, and this makes things much more complicated. So I won't tell you too much more, but these are kind of fun calculations. So The thing that I will tell you a little bit more about is how we get to upper bound. And the key idea of the upper bound will be to use these so-called higher order estimators. So here's the first key idea. So suppose we're thinking about estimating the Kate. If we make some smoothness assumptions, then one thing that you can imagine is that I can hope that in some little window around the point I'm interested in, because the Kate is very smooth, it's much smoother than all of my other nuisance functions, I can pretend like it's constant in some little window around the point I'm interested in. And so once you pretend that the Kate is constant, you can rewrite the Kate as some sort of average treatment effect over that little window. Right? So this functional is a little different. It's not the average treatment effect. It's something called the expected conditional covariance. If you've ever thought about conditional independence testing, this is the standard way of testing conditional independence, is to estimate some functional like the numerator. So if I was interested in knowing if A and Y are conditionally independent given X, one way to try to test this hypothesis would be to try to measure some notion of dependence between A and Y that is a conditional notion of dependence. And this quantity will be exactly the correct one to use for testing. And so that functional in the numerator, which is the expected conditional covariance, has a long history. It's a useful conditional independence measure. If A and Y were in fact binary, then it would measure for you the distance between. So if I take some distribution, if the expected conditional covariance is 0, that implies that these two things are conditionally independent given X. If the expected conditional covariance is not 0, then it will tell you how far from conditionally independent you are in a total variation sense. And so this functional has some long history again. And the key point for us will be, because we're assuming that tau is much smoother than the other nuisance functions, you can pretend like it looks like a constant. And then rather than estimate the average treatment effect, you can try to estimate this easier functional, which is this ratio of the expected conditional covariance and the expected variance. So the way that one does this is you start off with the first order estimator for, so let's say I just cared about estimating the expected conditional covariance. I would first start off with the first order estimator. It's the thing that's written here. It's, if you have to trust me on this, but the one-step corrected estimator has a simple form. It looks like you construct your pi hat and mu hat on a separate sample, and then you take an average of A minus pi hat times Y minus mu hat. That's the one-step corrected estimator. That's the doubly robust estimator for this functional. And then you're going to try to add to it a second order correction. So what's the intuition now? The intuition is, if you squinted at this, the bias of your first order estimate looks like this product over here. It looks like the product of the true pi minus pi hat times the true mu minus mu hat. And so the reason why the first order estimator is not optimal is that it has too much bias. So you can say, okay, what is its bias? Its bias will be exactly this term. And then you can say, can I try to construct an estimate for this quantity directly? And that's exactly what these higher order estimators do. They take a one-step estimator, they evaluate its bias and say, okay, can I try to estimate its bias and subtract it off? Okay, so if you work this out, it'll turn out that this so-called U statistic, now it'll be a second order U statistic rather than just be an average. It'll be a second order U statistic. Once you subtract it off, you will get a minimax optimal functional estimate. So this is the higher order estimator for the expected conditional covariance. Is everyone roughly okay? So high level, the first order estimator for the Kate is not optimal. You can construct the second order estimate. It looks like a second order U statistic with some careful design choices. Okay. So now let me summarize the first part of the talk, then try to take a step back and tell you a little bit about some other things. So the summary for the first part is that if you dig through this literature, there are lots of recent Kate estimators. So things, the DR learner that I told you about is just one of many, but it's not very well understood, at least till we started doing this, what the best way to benchmark these different estimators is. They all have different incomparable guarantees, and it's not clear if any of them are optimal. And it's not even clear what optimality means or why it's interesting. And so we gave some Minimax framework where we said, what does it mean to optimally estimate the Kate? What is the set of assumptions and so on? And then we did develop these higher order Kate estimators, and we gave what the Minimax rate was in this problem. Okay, and I'll conclude this part by saying there's lots of things that we don't really understand well enough. The higher order estimators are very brittle. They require you to know the covariate density or to estimate it fairly well, which again, you can imagine is not a very nice assumption, except in theory. So there's lots to do. Okay, so now I'm going to pause for a minute. If you have questions about this part, you should ask me now. Otherwise, well, if I've lost all of you, you can try to reset because I'll tell you about something else for the last bit.
We just can you also have politically normal estimator if you're just estimating this tau at a point? We always have this non-parametric rate.
You always have this non-parametric rate. Yeah, so the efficiency lower bound is never root n, it's always something slower than root n. So you can get something that is asymptotically normal, but then you'll need to under smooth somewhere. It's kind of like a non-parametric regression problem. Good. Yeah.
So why second order is not like
You could need, so what makes the second order enough here is that I assume that you know this density. If you don't know this density, then you will get some error that depends on how well you estimated that density, and that bias could be too high and you could try to estimate it and so on. So
even is there in the base
no, so there's our density functionals, so it's a little different. So there's the only thing to estimate is the density in their problem, but also they're looking at a quadratic functional, so it doesn't make any sense to look at higher order things. So what Berger and Massard did was they looked at just a general nonlinear transformation of the density, and then they showed that you would maybe typically need a third order correction. So what makes a second order correction sufficient here is this very strong assumption that you know the density. Okay, cool. Thank you. Other questions? Okay, so let's take a step back and just think about what we've seen so far. So what we've seen so far, I gave you two examples. One of them was this second order estimator for the kit, and the first thing was this DR learner, which is a first order estimator for the kit. This is an example of a very general thing that happens in functional estimation problems. The first order estimator will be something which is this one-step correction, this doubly robust thing, and it will achieve these agnostic error bounds. So the error bound looks the following way. You take your half of your data, you construct an estimate, say eta1 hat and eta2 hat of your nuisance functions, so whatever they are, and then you plug them into some formula, which is some sort of averaging on a separate sample, and then you get these agnostic error bounds. So this is, what do I mean by this? You get variances that look like 1 over n, and the rest of the error, which is some sort of bias term, looks like the product of the mean squared errors of how well you estimated these nuisance functions. Right? So what is nice about this error bound is that it doesn't depend in any way on smoothness or anything else of these nuisance functions. So it could be the case that I fit these nuisance functions using a deep neural network. So I estimated my propensity scores and my regression functions using some deep neural network on the second half of the sample, and I just plug it into this functional, whatever, this averaging of pseudo outcomes operation, and I get a functional estimate out of it, and it would inherit whatever nice properties the first stage had. So if your deep neural network was magically the right thing to do and it had low MSE, you don't care what went into that black box. Your functional estimation will achieve a rate which just gets better if you could solve a prediction problem well. Right? So this is nice. There are no structural assumptions essentially being used to prove this bound. Right? So this just happens to be, you just split your sample. On half of it, you estimate your nuisance functions. On the other half, you estimate your functional, and you get this kind of guarantee. There are no structural assumptions being used. And maybe particularly, this is very compatible with this black box way of thinking about functional estimation. I black box out some hard prediction problem. It's this hard, high-dimensional regression problem. I've black boxed it out to some deep neural network, and then I just use whatever it gave me as the output in order to estimate my functional, and I get some guarantee that looks like this. And the nice thing is that it just says, okay, if you solve the prediction problem well, you will get an accurate functional estimate. It doesn't depend particularly, you don't need smoothness, you don't need anything else. As long as you don't even need to be able to quantify why it was that you could solve that regression problem well. As long as you can guarantee me that you've solved it reasonably well, you will get a good functional estimate out of it. Okay, so this is sort of nice. You should contrast it with the second order estimator that I told you about for the kit, where I played very carefully with a lot of smoothness assumptions in order to design that estimator. Okay, and what was the drawback? Why did we need to introduce that second order estimator before? The reason was that the first order estimator is not minimax optimal, right? So if I assume some sort of holder structure, even if I estimate the nuisance functions optimally well. If I plug it into this first order estimator, I will not necessarily get an optimal functional estimate. Right? So this is somehow the trade-off. There's this nice, robust way of estimating functions, which is this one-step correction, which has all these nice magical agnostic properties, doesn't care about how you did your regression or whatever else. It doesn't care about any structural assumption whatsoever, but it's not necessarily minimax optimal. Right? On the other hand, maybe you should think about the higher order estimator as somehow doing something different. It's a U statistic, typically with some very careful undersmoothing. By undersmoothing, I mean it will somehow, if you think of the nuisance function estimates, they actually have much lower bias than variance, and then you do some averaging somewhere to balance them out. Right? So it's very carefully designed to exploit the holder type assumptions that you make. And they will be minimax optimal, but they're often very impractical. Right? So this is maybe the way to think about this general trade-off. There are these first order estimators, very practical, very easy to use. They have these nice robust error guarantees, and then but they're not optimal. And then there are these higher order estimators, which are optimal, at least over the standard classes that we work with in statistics, but they're not very practical. Okay, so everyone roughly okay? So you've seen some version of the story so far. Okay, so maybe this should motivate the following question. So what exactly are the limits of structure agnostic functional estimation? So if I'm not willing to make the assumption that my regression functions are holder smooth, and I want to maintain some sort of compatibility with these black box notions of prediction, right? So how well can I do, right? So maybe the first thing you should think about is, okay, how do I formalize this question? I kind of asked you something that vaguely maybe makes sense, but not clear that it's very formal. And maybe the other part is to try to answer these types of questions. So one of the goals of this higher order theory, so people have been working on higher order estimators for quite a while now, have been trying to bridge this gap between first order and higher order estimators, where trying to make higher order estimators more robust to black box nuisance estimates. And one question one can ask is, okay, is that feasible at all? And if I somehow manage to formalize this question of what is structure agnostic functional estimation, then what are optimal estimators that are structure agnostic? Is it that first order estimators are the only things that are structure agnostic and therefore optimal? Or are there other things and are they better? Okay, is everyone roughly on board? Okay, stop me if you have a question so far. Good. So, Arash, how much time do I have? 10 minutes. Okay, so good. So now let me try to formalize my question of what is structure agnostic functional estimation, and then try to tell you what is the best that one could hope to do. So here's, again, we'll start with this classic causal inference data structure. We'll think about some covariates, some treatment, and some outcome. And now let's just suppose I forget about the average treatment effect or the conditional average treatment effect. I focus on this simple functional that I told you a little bit about, this expected conditional covariance. So the thing that I want to estimate is the expected conditional covariance between A and Y given X. And so this is some notion of conditional dependence between A and Y. Okay, so we'll denote here pi as the propensity score and mu as this regression function. So these are the conditional expectations of A and Y given X respectively. So once you set this up, there are some natural estimators. If I'm interested in the expected conditional covariance, the plug-in estimator would be, you just write it out. It would be some function that looked like this. It would be the average of A and Y minus the average of pi hat and mu hat. And so you can just work it out. This will be the correct plug-in estimator. And then the first order estimator kind of tries to correct it. It looks like this. Looks now, I mean, it's just slightly different, but it has these second order guarantees that we like. And then the higher order estimator, again, you've seen it before. It's some sort of second order U statistic that now depends on A and Y. Right? So there are all these different estimators that one can write down for this functional. Now let's try to formalize what I mean by structure agnostic. So here's the idea. I'm going to imagine that I'm going to take one half of my data or a separate half of my data and pass it to some black box and ask it to solve these regression problems for me to try to estimate the propensity score and the regression function. Right? So let's suppose that all I want to assume now is not that these mu and pi are smooth, but rather whatever that black box is returns to me an accurate estimate of mu and pi. Right? So this is the assumption I want to make. I want to make it somehow compatible with this black box world. I'm just going to say some deep neural network can solve these prediction problems for me well. And so this is the assumption I would like to make. Mu hat is a good estimate of the true mu, and pi hat is a good estimate of the true pi. And so this is the assumption, and there's no additional smoothness assumptions that we're going to make. So now the question is, okay, what is the best that we can do? What is the minimax rate under just this assumption? And so if all I told you was, here are two pilot estimates of the propensity score and the regression function, they have some unknown accuracies, Rn and Sn. I don't know what those numbers are. The statistician does not. And all I want to know is, okay, how well can you estimate this functional? The functional is not necessarily smooth anymore. Okay, so you can now again ask this question via this minimax lens. So now I will define my statistical model the following way. I'm going to say any distribution where mu is within Rn of mu hat and pi is within Sn of pi hat is in my model. And I would like to know, okay, how well can you do in terms of estimating your expected conditional covariance in this model? And so what is the best possible estimator of the expected conditional covariance under only the assumption that whatever your black box is was Rn and Sn accurate? Is everyone okay? So you should contrast this with the usual functional estimation theory, which says mu and pi are smooth with Holder smoothness alpha and Holder smoothness beta, say. And so now I'm not going to assume that. Everyone good? Okay, so here's the result from the paper. So it just says, okay, if that's the only assumption that you're willing to make, then there's no hope for improving on the first order estimator. So this, in particular, the minimax rate in this model looks like 1 over n, which is the variance of the first order estimator, plus Rn times Sn, which is sort of the bias of the first order estimator. So the MSE kind of looks exactly like the error of the first order estimator. So you get this product of two errors, which is this double robustness thing that we highlighted before, and you get a variance term which looks like 1 over n. And essentially the theorem is just saying that whatever the first order estimator gets for you in this problem is optimal. So if you're not willing to make Holder type smoothness assumptions, then there's nothing more you could hope to do. Okay, so the key takeaway from this result is just that this first order estimator is adaptively minimax optimal. Adaptive meaning it doesn't need to know Rn and Sn, but it still gets a rate that depends on them and gets the best possible rate that could depend on them. And maybe the other takeaway is just all this higher order machinery is only useful when you're willing to make some other structural assumptions. If all you were willing to say was, I have a black box that solves some regression or prediction problem well for me, then that's not enough. At that point, the best you could do is to construct a first order estimate. And the way you should think about this is, if I made no assumptions whatsoever, then all of these functional estimation problems are impossible. But this assumption that my pilot estimates are accurate is a very weak structural assumption. It's some assumption. It doesn't give you that much structure in the problem, but it's exactly that structural assumption that the first order estimator is tailored to exploit. Okay. And maybe if you cared about other functionals in, say, the sequence model or in the white noise model, you would see some results in our paper for those two. Is everyone okay with what this result says? Okay. So the upper bound follows from some very standard ideas. I'll tell you one thing about the lower bound, but it's also, you follow the same high-level sketch as before. You try to construct some pair of mixture distributions, try to argue that their Hellinger distance is very small, and the separation between the parameters is very large. And the key thing is that what you're trying to prove is this Rn times Sn is a fundamental lower bound here. And the idea is that since you have not imposed any smoothness assumptions, then you can sort of wiggle your nuisance functions in some very arbitrary way. And this will help you in this construction. And so the key thing that will make it different from very classical constructions is that you no longer have smoothness constraints. So it makes it a little bit easier to construct lower bounds here. And that's maybe all I will say about this. And then let me just summarize now the second part of the talk, and then I'll stop and take questions if you have any. So maybe the summary for the second part is that these first order estimators are extremely popular. In econometrics, they go by the name double machine learning. It's a nice appealing name to try to summarize what is going on. It's just saying that you black box out some nuisance function estimation to some machine learning algorithm, and then you get causal estimates out of it if you're careful. Right? So it's very robust, it's very popular. And one of the main reasons why they're so popular is that they have these agnostic error bounds. And the main knock on these first order estimators for a long time has just been that there's no known setup where they're actually the right thing to do. So at least in the classical setups where you assume Holder type smoothness or you assume sparsity or something else, it'll turn out that the first order estimators are not optimal. And so even though they have these nice properties, they weren't really, it's not clear what exactly whether they're ever optimal. And so what we did was we gave some minimax formalization of this property of structure agnosticity. So we said, okay, this is this desirable property that these first order estimators have. Here's a formal way of saying what it is. And then try to say that, okay, if that's the only assumption that you're willing to make, then in fact, these estimators are optimal. And one way of interpreting this result is to say, okay, if you want to improve on these first order estimators, these very simple black box corrections, then you have to make some other set of structural assumptions and exploit them carefully. It's not possible to exploit them without imposing some more, to improve them without imposing some more assumptions. All right, so let me stop here. And if you'd like to see some more details, these are the two papers. Thank you.
Question? Also from the online audience. I can maybe ask one question. So like this agnostic part,
Yeah.
the way that you define the minimax, it's like related to the new hat, the new hats are estimators. So it's like,
Yeah, you should imagine.
it's like, so how do they define the parameter space? That's the question.
Yeah, so you should imagine that they're sort of constructed on a separate sample. And now the question is, okay, I'm just going to hand them to you and they're now going to be treated as fixed. And the true parameter is then set after you see the pilots. So it's a little bit strange of a framework, but it's sort of trying to. Yeah. Yeah.
A very simple question from a practitioner's perspective in terms of guidelines. The structure agnostic probably require fairly large sample sizes, especially given the fact that the independent samples in order to achieve good performance. Unless you put it functionally very simple, in that case, obviously, probably the further assumptions involved. So in practice, I mean, if you were to advise somebody who has a limited data set, how should they go?
So somehow, okay, so because I was talking about the theoretical properties, I sort of always said, just assume you split the sample and whatever. So one thing that is very nice about functional estimation, again, it's an observation that goes back to Bickel, which is that you can do this thing called cross-fitting. So that is, you estimate your nuisance on half of the data, you construct your functional estimate on the other half, and then swap the roles and you average. And then essentially there's, at least from a information perspective, you don't lose anything. You'll get efficient estimates doing this. And this is not true always, but for functional estimation problems, it's often true. And so maybe the practical advice would always be, you should try to use sample splitting, first order estimator with cross-fitting. And that's somehow the default thing that is very popular in econometrics and epidemiology and so on. So I mean, I think maybe the only thing is I sort of ignored this cross-fitting aspect because I didn't care so much about the constants in the theory, but in practice, that's a very useful idea.